Now that you're familiar with the notation, second order or even higher order partial derivatives, let's just try a couple of examples to make sure that you understand the process. You'll find this example in section 8.7 in the lecture notes. If you want to calculate all the second order partial derivatives of this function, you need to calculate f of xx, f of xy, f of yy, and f of yx. So there's 4. If you want to do that, the first step is always just calculating the first order partial derivatives. In this case, fx or df dx. You look at the function, you only care about the things that contain x, using chain rule and all the rules that should now be very familiar to you. In this case, you'd get minus 2 sine of 2x. And in this case, this does not depend on x. This does, but it's relatively simple. You get minus 2x, and then the rest is a constant. For the derivative in respect to y of f, this does not depend on y, but these two terms do. We just use chain rule, that's minus 5x squared e to the power of 5y plus 6y. These are the first order partial derivatives, which you already knew how to calculate. And step number 2 and final will be just about differentiating these again. If we start with fxx, all we do is we apply the partial derivative operator to fx. You can even just write it explicitly. This is what we're doing. And whenever there is a next term, we differentiate again. In this case, we would get minus 4 cos of 2x. And in this case, we would get minus 2e to the power of 5y. That's one of the partial derivatives. We get yy as just applying d dy to f of y. In this case, we are applying it to this, and we would get minus 25x squared e to the power of 5y plus 6. And for the other derivatives, we're going to have to make some space, so this will be the one sacrificed. And let's calculate fxy. If you remember the notation, this is the same as applying d dy to fx. And if we do this, the terms now that only depend on x don't count, so there's a 0 here, and here we just use chain rule, and we will get minus 10x e to the power of 5e. And if we do the same for f of yx, this is applying d dx to fy. We also get minus 10x e to the power of 5y. And this would conclude the problem, because we've calculated all 4 partial derivatives, and we've even noticed that the cross-term second order partial derivatives are the same as they are for most functions. As I've already pointed out in a previous video, for most functions we will find that the order, if you've calculated first the partial derivative in respect to x and then y, or first y and then x, you will get the same answer. And therefore, if you do that, and if you compare them, if they are the same, that's good news. You probably did everything correctly. If they're not the same, I would encourage you to look back and try to find your mistake, because it is almost guaranteed that it is there. As you can see, calculating second order or even higher order partial derivatives is relatively simple. You just need to apply the differentiation rules, which you now know very well, and to identify which variable you're differentiating against. Provided you do that and you understand the notation, then partial derivatives can be relatively easy. But apart from being easy, they're also incredibly useful, especially second order partial derivatives, because they will allow us to come back to these four stationary points and classify them in the next video.